Okay, we're recording. Okay, so here's where we're picking up from last time. I guess before I start in with the math, let me just remind everybody from the schedule here. Here's our lecture schedule. That today, being Wednesday the 8th, the material for today, you'll notice by the color coding, is fair game for the second exam. It is not fair game for tomorrow, for Friday's exam. So it's kind of a weird circumstance, but of course the alternative would be to have today's material be fair game, and I don't think anybody wants that. So anyway, weird that we're going to be covering material that's not fair game for the exam. It's not part of the homework that's due on Friday, but again, it's better than the alternative, so here we are. So, okay, but I will point out that notice exam 2 is not that far away. Right? What's that, about a month, right? A little over a month. So, anyway, for whatever that's worth. Alrighty. Okay, so, last time we were talking about the chain rule. And here's the chain rule as applied to the composition of the following two functions. You see I've got f, where x's go in and y's come out. And so there's its partial. Its derivative matrix full of partials. And then here's g. The outputs from f, namely the y's, go in to this function, and then the z's come out. And its derivative matrix comes second. And again, keep in mind the whole left and right thing. This one acts first. This one acts second. The green one, by acting first, is on the right in matrix algebra. And the blue one acting second is on the left in matrix algebra. So anyway, it's awkward and confusing, but please be careful and keep that straight. Okay, that said, of course, this product gives us the derivative matrix for the composition, which takes x's as inputs and gives z's as outputs. And so its derivative matrix is going to be these partials here of z's with respect to x's. Okay, so all this is the chain rule. It's just derivative of the compositions, the product of the individual derivatives, and, of course, derivatives are matrices. Okay, so what I want to do, though, is focus on looking at one particular element of this composition derivative matrix. So I'm going to look at the partial of zi with respect to xj. That's in the ith row and the jth column of this matrix. And, okay, well, the way we compute that is by doing a dot product of the ith row of the left matrix with the jth column of the right matrix, and I can just do that right here. Here's the green entries, here's the blue entries, and that's how we compute dot products. Right? Just multiply and add. So what we have then, one could take this as a sort of an alternative form of the chain rule. And the idea, the pros and cons, the con is that it's kind of a weird long formula with just a ton of notation. It's not as compact, and it's not as simple as multiply the derivative matrices. I mean, this could not be easier, right? So this one is bulkier and longer, and there's lots of subscripts and stuff, and it's kind of annoying. What's good about it is that if it should happen to be that all you actually need is one partial derivative, if that's all you're interested in, just the one. I don't care about any of this stuff over here. I don't need to know all of those parts. I just want the one partial derivative only. Then this gives you that one partial derivative, and you don't have to compute a bunch of partial derivatives around here that aren't relevant to this specific calculation, and you don't have to compute any of these. It saves you a bunch of partial derivatives you don't have to compute. So that's nice, right? It's a good thing. All right. So there's that. Now, I do want to give you a warning with this formula. A lot of students fall into the little trap, what I'm going to call a trap here. A lot of students will look at this formula. Look at this formula, and kind of, as they're writing it, they'll get to about here and then stop, perhaps thinking that, okay, well, this and that cancel, and that leaves me with the partial of zi, it would seem, with respect to xj. We're done. Why do we even have the rest of that? Everybody see the temptation? So what we have here is a consequence of what I'm going to call unfortunate notation. It's the notation's fault. Right? Now, you've probably heard me say this before. Maybe you have, maybe. Anyway, but it's tempting to look at partial derivatives and think of it as a fraction, and it's kind of a fraction, but this is not a fraction of things which exist independently on their own and always carry the same meaning no matter what. It's not. Right? So it's best, I think, simply to think of partial derivatives as just not being fractions. We write them as fractions. There is a fraction involved in their calculation, but they aren't fractions. Okay, so here's the point. Let's look at this first term here and think about what's happening and what does this represent and each of its appearances in this term. So here, this is part of a partial derivative. I'm taking a partial of zi, and partial derivatives means I'm going to hold all the other input variables constant. And so in particular, this one here says how much y1 changes with the understanding that the other y variables are constant. So this is a participant in a story, in a scenario. Right? And in the scenario that goes into this calculation, the other y variables are constant. All right, now let's put a pin in that. Let's come over here and look at the other one. Let's look at this partial partial y1, excuse me. What's going on there with that? Well, this is part of a totally different story in which, well, we're taking a partial derivative with respect to xj, and that means that we're going to hold all the other x variables constant, and then we're going to change xj. And here's the deal. If you change xj, well, all of the y variables are functions of xj, among other variables as well. But all of those other y variables are functions of xj. If you change xj, all of the y variables are going to change, right? So this thing here is, again, part of a story. This is part of a scenario where we're computing this partial derivative, and in which story these y variables are not constant. So this is two different stories, right? And you can't compare or relate the participants in two different scenarios, right? Like they're the same thing. I mean, just imagine you're taking a test and, question 1 has a couple of variables in it, x's, y's, and z's, something like that. And then you go to question 2, and it also has, totally different algebra, but the variables are also x, y, and z. You can't use information from question 1 about what x is and use that in question 2. They're totally different questions, right? Totally different scenarios. Likewise here, it just does not make any sense to view these as being the same thing, and you cannot cancel them. Does that make sense? Is everybody happy with that? It's a very dangerous little landmine. So many students on past exams will write down this and do that little cancel, and it's indicative of a complete misunderstanding of the chain rule. Right? So please don't step on that landmine. Okay. Alrighty. So moving along, here's a way to think about it. This is how I like to think about it anyway. And by the way, this is also very computationally useful. So we're going to rely on this perspective, not just for intuition, but also for computations. I like to think of this as representing what I call propagation of changes along various different paths between the variables in question. So here we go. We are going to vary xj with the understanding that all these other variables over here are all going to be held constant. Right? We're going to vary xj. And I'm interested in how zi changes, so I'll be looking at zi as an output. So xj changes. What happens? And well, one thing that happens is changes in xj will cause changes in y1. But here's the thing. Then when y1 changes, the changing of y1 will also cause a change in Zi. So this is what I call a change propagating, right? It's propagated through these different arrows from changes in Xj to an eventual change in Zi along this path going through Y1, or you might say by way of this intermediate variable Y1 that's in between them. Right? So you got changes that propagate along this path, and then, now here's the thing, simultaneously to that, in addition, changes to Xj cause changes to Y2, and changes to Y2 also contribute to changes in Zi. So you have a simultaneous propagation of a change through this other path. Said differently, through this other intermediate variable, etc. And so, in fact, what we have here, we have a bunch of different paths along which changes can propagate. Said differently, we have a bunch of different intermediate variables through which changes can propagate. And now let's try to figure out what each one of them means. Let's look at this first one. When if I change Xj and then want to know how much does Y1 change as a result, well, that's a partial derivative. How much does Y1 change per unit change in Xj? That is described by that partial derivative. Said differently, the factor that you multiply by the input change to get the output change is that partial derivative. But then furthermore, don't forget, not only does Y1 change by a factor increased amount, but then that causes Zi to change by another factor increased amount. And again, that's another partial derivative. How Zi changes with Y1 is that right there. So the idea then, is that each path corresponds to a term. Each path is made up of individual steps, you might say. Each one of those steps represents a factor. That's a step. That's a factor. Everybody on board? So, likewise for the other paths, and for each, okay, let's see here. So for this, I want to get the colors to match up. For this path, we have that term, and then, of course, there's a second path and a third path and a fourth path, etc. That's additional terms like that. And then eventually, lastly, we'll look at that path, which corresponds to this term. So this entire equation here is really just kind of a representation of how changes propagate from the input variable to the output variable by way of the different intermediate variables. What do you think? All right. Okay. All right. So what this means then is if you want to write down the chain rule as pertains to a particular single partial derivative, really all you have to do is identify what are your intermediate variables. You're going to get a term corresponding to each one of those intermediate variables. For example, the Y1 intermediate variable, well, it gives you what I'm going to call a Y1 term. Right? And then, et cetera, et cetera. And then the Ym intermediate variable gives you what I think should be called the Ym term. So just keep track of your intermediate variables, write down terms correspondingly, and off you go. And you don't have to write down all the matrices and do the matrix multiplication and all that. It can add up to a lot of tedium. Okay. All right. So here's an example. We've got the y's are functions of the x's, and then the z's are functions of the y's. It's our usual kind of, most convenient, most alphabetically satisfying, you might say, arrangement of the variables. And here's my diagram that represents it. Now, keep in mind, this is just a shorthand representing that I'm composing two functions. And it is very important to remember, you are composing functions here. What comes out of f is going in to g. Right? Okay, so this is my representation of the y's being functions of the x's, and this is my representation of the z's being functions of the y's. Does everybody see how I get this diagram? Okay. Alrighty. So, the question asks me to compute this partial derivative, partial of z2 with respect to x2. Alright, so x2 is the input variable that's changing. Let's see, z2 is the output variable that's changing. I see now what I've been asked to compute. Right, partial of this with respect to that. It's a single element of the derivative matrix, I suppose, but wouldn't that be inconvenient to write down? So I'm just going to write down just the chain rule for this one partial derivative by, again, looking at intermediate variables and looking at sort of paths, if you will. So one intermediate variable is y1, representing the path, the propagation path through y1. And here's my y1 term. And here's another path, intermediate variable y2, representing propagation through that path by way of y2, and that gives us our y2 term. And then it's just a matter of looking at the functions and what do we know about the functions and actually writing down some partial derivatives. And that's the easy part, taking the various partials. Let's see here, we'll do a couple of them. What is the partial of z2 with respect to y1? Well, z2 is that. What's the partial of that z2? What's the partial of y1 cubed with respect to y1? Well, it's 3y1 squared. So easy partial derivatives. What do you think? Is everybody with me? Repeat for the other factors. All right, so it's a nice trick. Okay, moving along. I do want to give you a warning about confusion of variables. This is an easy mistake to make, I'll say. I'm going to start with a single variable example. I really like when there is a good single variable analogy. I kind of like making those connections. I think it makes things relatable. So let's consider this function here. F of x is x squared. Perfectly good function. Not a thing wrong with it. Here's a second function. G of x is x cubed. Perfectly good function. Not a thing wrong with it. Nothing's bad yet. But then I'm going to say, what is the derivative of this composition? And as soon as we say we have a composition, there's actually something bad now going on in the way this question's been phrased. And let's ignore that for the moment. Let's proceed blindly. The shortcut, rough, easy way to say it is that a derivative of a composition is a product of derivatives. Okay, so fine. So we write that down. G prime times f prime. G prime is 3x squared. F prime is 2x. And so we get as our answer 6x cubed, which of course is wrong. Okay, now it's because I played a little too fast and loose with the pithy phrasing of the single variable chain rule. Now here's a more careful development where I have to recognize that the derivative of the second function has to be evaluated at the first function, and so g prime is 3 times the square of whatever its input is. The input is f of x, which is x squared. Right? So there's g prime of f of x. Everybody happy? Everybody? Okay. And then times f prime, blah, 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 and right answer. Okay. And you'll notice I've got this one, the first one is labeled as wrong because it's wrong. The second one I have labeled as valid. But I don't think this is a good way to do it. I think there's still something wrong with the way the question's been phrased. It's fundamentally doing what I call confusing variables, standard term, by the way. We see this most easily, I think, by actually drawing what we mean when we say a composition. If you're going to compose G and F, okay, well here you go, there's F, there's G, and if we're going to give names to the variables in these various places, as soon as I call this X, right, then X is here. I can't then also use x to represent the input for the g function, because the input for the g function has to be the output for the f function. Now x is playing both the input and the output for the same function. That does not make any sense. It's just, that's confusing, right? At best, confusing. So this very simple solution is just don't confuse the variables. Pick a new dummy variable. Let's have g be written as a function of y, let's say. Whatever, doesn't really matter what variable you use, but just because of the fact that we're viewing f as being a function of x, I really, really ought to reconceive of g as being a function of, well, whatever the output from f is going to be called, and it's definitely not going to be x. So in this case, I'm using y. What do you think? Is everybody on board? Is everybody see the problem and how this renaming kind of fixes the problem? So here's the beautiful thing about it. If you do this, if you avoid your confusion of variables, then you can go back to your pithy, rolls off the tongue point of view of the chain rule. Yeah, the derivative of a composition is the product of the derivatives. And just be as fast and loose as you want. G prime, okay, well, the derivative of y cubed is 3y squared. Right? I'm not paying attention to where I'm evaluating it. The derivative of f is 2x, no problem. And not paying attention at all, notice I end up with this product equaling this, and of course I need my answer to be in terms of x, so I've got to figure out what am I going to do with this y. How am I going to rewrite that y? Well, y is f of x. The notation, the choice of variables, keeps track for me of this whole business about evaluate at the appropriate place. So it's like it's like having the rails on the sides of the bowling lane. It keeps you on track for you. Does that make sense? All right, and of course we get the right answer. Okay, so I just want to point out that the same is true of the multivariable chain rule, and it's somehow a little bit more obscure and confusing when you're doing the multivariable chain rule. I mean, I think most of y'all would not make this mistake here in single variable calculus. But again, it has happened historically quite a bit, more in the distant past, because I've been making a bigger deal out of it in the recent past. But a lot of students kind of forget this and will see multivariable functions written in terms of the same input variables and kind of forget about what's actually happening and that they're confusing their variables. Right? Multivariable example, again, functions given, and I am going to draw a diagram. Okay, so I've got f is a function of two input variables. Fine, it has two outputs. What am I going to call these outputs? Well, those outputs, I can't call them x and y. That'd be nonsense. So I'm going to call them u and v. And having called those outputs u and v, that forces me to rewrite g in terms of u and v. Now, it's the same function here. I didn't really do anything to the function, right? It's 2 times the second variable squared, comma, 3 times the first variable squared plus 1. It's this exact same function, just written in terms of different dummy variables. And with that having been done, I can now proceed pretty conveniently. There's the derivative matrix for f. There's the derivative matrix for g. The derivative of the composition is the product. And there's therefore what I need to multiply, and I suppose I could start multiplying that all out, but let me remember before the algebra gets out of hand, that this u right there, we can remember what that u is. That u, you can see it right there. It's the first output from the f function. So it's x squared plus y squared. What do you think? Everybody okay? All right. Okay. And likewise for the V, and then you could multiply this out if appropriate. Anyway, as far as this example is concerned, I think we've seen what we need to see, so I'm not going to multiply it out. Okay. All right. Okay. Now here is another nasty little problem. These diagrams that we draw. Let me come back up here and remind you. Diagrams like this one, right? I draw, variables being related by arrows. Don't forget, this is a shorthand for a composition. That means that there's actually a function there called f. F has input variables and output variables. Then, don't forget, there's actually a function here, g, which has input variables and output variables. And when I say that I'm composing them, right? Composing means that the outputs from f are exactly the inputs for G. That's what it means to compose functions, right? What comes out of the one has to go in to the next. Okay. All right. So, fine, no problem. But, you'll write down stuff like this diagram right here. Perfectly fine. No problem. You can see I've got my first function. The y's are the functions of the x's. And second function, the z's are functions of the y's. No problem. Right, everything fits. This is actually a composition of functions because I can identify what the functions are in the diagram. Please don't make the mistake of losing track of that and just kind of feeling like you can draw any sort of a diagram that you want that connects variables, like any sort of a tree structure or something, and that's a valid diagram to which you can apply this intermediate variables business. It's not, right? So you got to be really careful about that. What are the functions in this picture here? And when I say what are the functions in this composition, what I mean is it, well, first of all, what's a function of what? And are the inputs from the one function, the second function, are they exactly the outputs from the first function? And, well, we've just got a nasty problem here because I might say, for example, that, okay, well, these are functions of those. But I just can't say that these are functions of just those. They're not, right? I mean, this also depends on x1. But then it's tempting to say, okay, then maybe these are functions of those, but that's not what a composition is, right? Again, with a composition, the outputs from the first function have to be exactly, precisely the inputs for the second, and that's not what is happening in the way I've got things grouped here. There's just no way to make sense out of this to satisfy the rules, the requirements of that this has to be a shorthand representation of actually a composition of functions. So here's a related question, just to show how nonsensical this is. Let's ask the question: what should partial of z1 with respect to x1 mean? And a lot of students would say, okay, well, we've got z1, and it's a function of all these variables, and I want to take the partial of that z1. Fine. I'm going to take the partial with respect to x1. That means that I'm going to let that be the variable, and then I'm going to have y1 and y2 be constant. And that's not possible. Right? If you vary x1, y1's going to change. y2 is going to change. You can't hold it constant. So the whole thing is just this is a mess. Everybody see what I'm talking about? So we got to avoid as much as humanly possible confusing messes. So let me show you how to fix that. If you have formulas given, for example, these. Colors. For example, these formulas right here are formulas that it would be tempting to represent with a diagram like that. Right? And so you notice, for example, that I've got y1 as a function of x1 and x2. right? And then we've got y2 is a function of x1 and x2. And then we've got z1 seems to be a function of x1, y1, and y2, etc. Right? So this diagram seems, at a casual glance, to be what I should write to represent these equations. But again, previously noted, this is garbage. So here's the way we fix it. The fix is pretty straightforward. Just recognize that I can't have this be a function of that and these. So I'm just going to make a new variable, x1 star. It's just x1, right? The formula for x1 star is that it is x1. But by introducing that as a distinct variable, right, now I've got a satisfactory diagram. And all of these are functions of those. No problem. Right? And all of these are functions of those. In particular, z1 is a function of these three variables. No confusion of variables, because x1 star is an output from the original function, as it should be. Everybody with me? Okay. Now, as such, I've got to abandon this equation and rewrite it again in terms of x1 star instead of x1. Right, so now I have these four equations instead of the original four, and that's just really no issue at all. I've got a perfectly satisfactory diagram representing a composition of actual functions. There's no confusion of variables. We're in business. And let's compute, for example, partial of z1 with respect to x1. There they are. And I've got three paths, three intermediate variables. That gives me three terms. Right? We can notice that well, look, this function here is a really easy function. I mean, on purpose, deliberately, x1 star being just x1, that makes this this is just a 1 right there. Partial of x1 star with respect to x1. Well, it's just 1. So that factor can kind of it can just kind of disappear because it's just a factor of 1. Okay. How we doing? Is everybody happy? Okay. So please heads up on this, and don't write down a diagram that doesn't represent anything that we can actually interpret. Okay. All right. Moving along. Second derivatives. So we already made this observation previously. If you have a function of x and y, right, then its partials also functions of x and y, and you can talk about their partials. Okay, so let's see an example where this comes into play in the context of the chain rule. By the way, this is a classic first example. It's in most textbooks on this subject. It's about polar coordinates. So we've got, you'll notice here, z being a function of x and y, but then of course x and y are functions of r and theta in the what I'm going to call the usual polar coordinate way. All right, so I have a composition here, and here's my diagram. And a reasonable question to ask: in this composition, z is a function of r and theta, and if it's a function of r and theta, then I can talk about its partials, but then I can talk about the partials. Let's compute, and in particular, let's compute the second partial with respect to r. Okay. All right. Well, the first partial is no big deal. Partial of z with respect to r. We have two paths. We have the x path. There's the x term. We have a y path we have a y term. Good news, some of these calculations are easy to do. Partial of x with respect to r. We have an explicit formula for x in terms of r. It's r cosine theta. So that's an easy partial. We can just write it down. It's just cosine theta. And then likewise, partial of y with respect to r sine theta. And then furthermore, don't forget we have these notational conveniences, and I can rewrite that as zx, and I can rewrite this as zy. All right, now is everybody with me so far? This is just a single partial. Haven't gotten to the second partial yet. Okay, so now let's take that second partial, and let's see here. The second partial, of course, is the r partial of the r partial. The r partial that we just computed, then, is what I'm taking another r partial of. And let's see here, a nice little lucky break. Let's think about this action of taking an r partial. Taking an r partial means, easy to lose track of this, but it means that theta is a constant. Right? So theta is a constant. That means that cosine theta is a constant, sine theta is a constant, and constants, I can play this trick right here, kind of separate, factor those out. They're just constants after all. And I find myself then looking at, by the way, I did that kind of fast. Is everybody okay with that? Everybody see what I mean? Because we're taking an r partial, we know theta is constant, and that's what allows us to treat these factors as constants. Okay. Okay, so here's where it gets tricky. What do I do with this thing? What is the partial of zx with respect to r? How do I take a partial, do I take a partial of an arrow with respect to a variable? That's not a thing. We haven't talked about, that doesn't make any sense. Right? Where on this diagram is zx? Doesn't appear on this diagram. So we're kind of out of luck. Until we recall this note up here at the very beginning. If z is a function of xy, zx is a function of x and y. And we can actually document that on our diagram. Here we go. Zx is, and I've got it listed as such, a function of x and y. So I'm adding to my diagram. My diagram did not previously recognize zx's role in this story. So I'm going to add to my diagram to make that recognition of where is zx, what is it a function of? It's a function of x and y. We put it there on the diagram. Is that all right? By the way, this is the way I do this stuff. This is my personal take. I don't think I can't remember if this is in the book. I don't think it is. So this is just my take. No, this is definitely not in the book. Excuse me. Definitely not in the book. In fact, I'm remembering now. This is part of the included material. If you look at the content syllabus, this is in that column of stuff that should be in the book but isn't, and that is fair game for the course. Okay. All right. So likewise, what is zy? Well, it's a function of x and y, just like z is. So we recognize that on the diagram. And now we've got a clear path forward. You want to take the partial, you say, of zx with respect to r. All right, no problem. I see two paths. There's the x path, and there's the y path. And we can write them down. Here's the x term. And here's the y term. And notice in each we're talking about zx with respect to r. Okay, so I want to pause on this. What do you think? Does everybody see the color coding is laying out what's relating to what in what way? Is everybody happy with that? Okay, so of course, all of this is just a chain rule intermediate variables expansion of that one partial derivative. Don't forget your constant that, of course, comes along for the ride. Right? And then you've got now a whole nother chain rule partial derivative to be dealt with. Apparently here we want to take the partial of zy with respect to, zy with respect to r. So for this second sort of new partial, there's our diagram, there's our chain rule story, and we have an x path and we have a y path. And as before, this constant doesn't go anywhere. What do you think? Is everybody okay with this? Everybody see what's happening? Okay. Now, I do want to call your attention to one thing. This is a good rule to try to follow when you're doing this kind of thing. Notice I did this nice and slow, right? Don't try to rush through this. A lot of students will try to go kind of straight from here down to here and just kind of keep track of that all in your head. You're going to get confused. You're going to leave something out. There's too much going on. So take your time, right? Do whatever algebra you've got to do to get it down to where these partials that you're going to need the chain rule for are written down independently, separately. No junk in the way that you're going to have to keep track of while you're applying the chain rule. There's enough going on while you're trying to apply the chain rule. Yeah.
So in this case, we would just leave Cx alone since it's just a function of x and y.
There's nothing we can do with it because z is a function of just x and y, and I don't know what the function is, and so I can't compute it. So it just is what it is. Mm-hmm. Yeah. Right. There's nothing to be done. Right. Good. Anybody else? Okay, it's all over with the shouting at this point. Partial of zx with respect to x. Well, that's zxx. And again, I can't simplify that because I don't know anything else about what that function is. It's just generically, it's zxx. Partial of x with respect to r, still cosine theta. More notational rewrite, followed by another easy partial. Don't forget your factor that came along for the ride. Ditto over here, right? And with all that done, you can kind of multiply, collect terms, etc., and this is what you end up with as your result. So if you know, if you are given, a function written in terms of x and y, but for whatever reason you want its r second partial, right? Knowing just the function in terms of x and y, you can take those partials of the function in terms of x and y, and then this is the extra stuff you have to add on to get what you want. So, nice general rule. Okay, let me show you a place that this gets used. This is going to be a little bit of a physics discussion. This is going to be a discussion of math that applies to physics. And we're going to talk about this thing called the Laplacian operator, which is this great big formula right here. It's the sum of the three rectangular second partials. There are extremely good reasons for why this is of natural interest in physics and engineering. So short answer, if you want to know how waves flow in three-dimensional space, well, the equation relies critically on the Laplacian operator. If you want to understand how heat flows from hot things to cold things, but in three-dimensional space, right? Y'all have all done the sort of the single variable calculus. I have a hot penny and a cold penny, and I just put them in contact, and we assume the pennies are infinitely thin. That kind of thing, where it's just a one-dimensional situation. But in a three-dimensional situation, heat doesn't just flow in one direction; it flows kind of outward in all directions, and it gets to be a nasty problem. The heat equation, we call it, It's written in terms of the Laplacian operator, etc. Schrodinger's equation as well has the Laplacian operator in it. Okay, so this is a big deal. And the problem with writing it in this way, even though it's very natural to write it in this way in a lot of circumstances, very often the function you're applying it to might be much more natural in spherical coordinates. So we've got a rectangular operator, but we've got a spherical function we want to apply it to. How do we deal with that? And the answer is we compute something called the spherical Laplacian. We take this Laplacian and we can rewrite it as, well, this monster, as it turns out. And the way you can do this is you can just straight up compute, for example, the partial of f with respect to rho. Here's f, there's rho. In this diagram of variables, right, we have a composition where the f is a function of rectangular is a function of spherical, all in the usual way. You can use methods from the previous page, right, to compute that partial. And likewise for this, and likewise, now here you're going to have to compute a second partial with respect to theta. Again, just, methods from the previous page. There's f, there's theta. You can compute that second partial. And with all of those things computed, with this computed and that, you can plug all of that into here, and sure enough, it works. All right, so you can, I'm not saying you should do this. This is a lot of work. It's very tedious, and this would fill up a couple of pages, I think, of algebra, even if you're pretty compact. This is a lot of effort to do this. But I want to show you how nice it is to have the spherical Laplacian. So here's a very generic story of I want to understand gravitational potentials, for example. This also applies to electric potentials, but whatever. So I've got gravitational potential energy, and in the absence of mass, gravitational potential energy satisfies this equation, that the Laplacian is 0, away from where mass is. Okay, so what functions satisfy this rule? What functions can be gravitational potentials? Pretty natural question, right? And so we might want to try, for example, to test something. Let's try this function right here, and let's plug it into there and see if it works. And now you'll notice this function I've written two ways. I've written it on the one hand, I've written it in rectangular coordinates, but look how much easier it is in spherical coordinates. Way easier. Why? Because gravity tends to be intrinsically a radial thing. Right? Spherical coordinates is set up in a kind of a radial way. It's, angles define a direction, and then rho defines distance in that direction. It's intrinsically kind of radial, as is gravity. So it's, the physical world imposes on us then a need to write things in spherical coordinates sometimes. And look again, rectangular coordinates, for all of its merits, it's pretty awkward to write this down. So, okay, here's our options. I can write down the rectangular Laplacian and the rectangular f and compute that and hope I get 0. And you can probably see this coming. That's going to be super tedious because I've got a fraction and a square root in the denominator, no less. And oh my gosh, it's such a pain to crank this out. I've done it. Right, more than once, and it's not the worst calculation I've ever done, but it's a pain, and to be avoided if you possibly can. So here's our other option. I can use the spherical Laplacian and the spherical formula for f, and I want to show you how easy this turns out to be. This is really not bad at all. It's really nice. Let's look at this first term as applies to this function. Very first thing I got to do is apparently compute the rho partial of this thing. Well, that's easy. Right, I'm going to get negative k over rho squared, which I'm then going to multiply by rho squared. That gives me negative k, which I then take a derivative of. 0, boom, walk away. Right? That term's gone. I didn't even have to write anything down. That was easy. Next, I've got to apply this scary-looking term to that function. And the very first thing that I need to do then is take the phi partial of an expression that doesn't have any phi's in it. 0, walk away. And then finally, this applied to that. Theta partial. There's no thetas in there. 0, walk away. We're done. This works. This is a lot easier, right? So this is an example of a couple things. First of all, it's an example of why it's really nice to be able to understand how to use second derivative chain rule for applications to things like spherical coordinates. And I also think this is a nice inadvertent lesson in why it's important to use, if you're doing physics and engineering, use the right coordinate system. Right? This is a huge deal. Do not try to solve Schrödinger's equation for a hydrogen atom, which is, radial potential, in rectangular coordinates. Oh, no, not at all. No, that would be a nightmare. No, for God's sakes, do it in spherical coordinates. Pick the right coordinate system for the right job. Okay, that's a good stopping point. See y'all later. Have a good one. Good luck studying for the test on Friday.